All right, so as I said, last week we have discussed the concept of local coordinates and global coordinates and how to basically relate elements in the local space to the global space. I'm just going to summarize things which we did for the two-noded elements. So for the two-noded elements, we now write the displacement in terms of the shape function, just like before. So U is N1, N2 multiplied by U1 and U2. Now, obviously, the shape functions has changed. I'm not going to write them down here because it's just not necessary now. The U point we did last week, I probably just write down in blue so that you can remember that these are new steps. So x is equal to N1, N2, X1, and X2. So this is something new we didn't have before. And then we went into the strain and the stress. So the strain, I'm going to write the strain in different color because today we are going to move into 2 dimensions, and things which I'm going to come into with depth in this week, I'm going to highlight with red. So the strain is the derivative of the stress and basically the B matrix multiplied with the displacement. Now the B matrix is just the derivative of N1 with respect to X. Say this is the X here, and the derivative of N2 with respect to X. And then again, last week, what we did, we said that we have the Jacobian matrix. So this is also new. So the Jacobian matrix is the derivative of X with respect to Psi. So this is X here. The derivative of X with respect to Psi is just the same like the derivative of U with respect to X. So this is nothing different than that. So this is the Jacobian matrix. And then we said the B matrix here is written in this way. So it is N1. I probably just write that also in blue because this is also new. So it is basically the derivative of N1 with respect to X and the derivative of N2 with respect to X are simply the inverse of the Jacobian multiplied by the derivative of N1 with respect to Psi and the derivative of N2 with respect to Psi. So this is also new. And once we have the Jacobian, we have the B matrix. And once we have that, we can do the stiffness matrix. I'm just going to write the stiffness matrix as well, is equal to A. For the time being, I'm just going to revert back to the older version of the stiffness matrix. So I'm not putting E in here just yet. It is the B transpose multiplied with D. We said that in the 1D case, D is simply elasticity modulus, but since we are going to discuss the 2D case, I'm just going to put it in red for now, multiplied by the determinant of the Jacobian. The determinant of the Jacobian is in U, so I'm just going to put it in blue now. And then it is the Xi. Actually, these boundaries of the integral are also not +1 to -1, so I'm just going to put them in blue as well, because they are in U. I mean, before we had that between 0 and L, now we have it between -1 to +1. Okay, so this is basically what we have done last week. Everything I have in blue here is the extra information we discussed last week. Now, I mean, if you want, I also can write the shape function. So N1 is half 1 minus Xi, and N2 is half 1 plus Xi. So these shape functions, but in reality, that shape functions are pretty much the same like what we have done. If it is X or if it is Xi, it doesn't make any real difference at all. So So this is it. Okay. So now I'm going to move to 2 dimensions. What we are going to do today, we are going to discuss the 2-dimensional problem. We are going to shift everything we have learned in 1D into a 2D case. All right. So everything we have learned so far has been working in 1D. Now I'm going to introduce changes that will shift everything into the 2D. Now the changes I'm going to introduce today are mainly related to the elasticity modulus, the strain and the material properties. So this constitutive relation, the elasticity modulus. We said this is elasticity modulus. So the D matrix is simply the elasticity modulus. And this relation between this displacement and the coordinate is not going to be just u. I mean, first of all, you know that there will be displacement happening in 2 dimensions. So displacement in the x and displacement in the y direction. So just having derivative with respect to x would not make sense. And if we're talking about the material properties are more complex in 2D than in 1D. Okay. So do you have any questions before I move to the lecture today? All right, so in this case, let us move into lecture. All right, so before I get into explaining the relation between the material, so the relation between the stress and the strain, so this material properties, I'm going to show you the material, I'm sure going to show you the stress and the strain in their full extent. Now I'm going to come back to discussing the stress and the strain when discussing the feedback for the course. But if you look into the stress in 3D, it actually consists of 9 independent components. I mean, it is a 3x3 matrix. Actually, it is a 3x3 tensor. But for the time being, let us call this a matrix. So it is a 3x3 matrix. And in the most general case, this is not a symmetric one. So, I mean, in what you have studied so far, you know that sigma 1, 2 is equal to sigma 2, 1. So these 2 components are the same. And you know that this one and this one is the same, and this one and this one are the same. So what you have learned so far is that these components are the only independent component. But let us start from the most general case. Let us start from a situation where you have all the components to be independent, and then you have 9 independent components. The same story is true for the strain. And if you want to connect them, you have, I mean, this is a 2x2 matrix. So this is a 3x3 matrix. This is a 3x3 matrix. And if you want to connect them, you need to have a matrix that is 4-dimensional. That includes 4 dimensions. So it is 3x3x3x3. Now, in total, this one, I mean, try to imagine it, that is happening in 4 dimensions. It's not happening in 2 dimensions. So this is something you can easily write because this is in 2 dimensions. But we are talking now about a matrix that is actually 4-dimensional. See, this is the strain. I'm going to mention that. So this is the strain here. And this is the stress. Now you need something that connects them. If we're talking in 1 dimension, sigma is related to the stress using the elasticity modulus. This is the only connection between them. Yeah. Now think about, you have a 3 components vector. So this is sigma 1, sigma 2, and sigma 3. And then you have the strain. It is E1, E2, and E3. And to connect them, you need to have a 3x3 matrix. So I'm going to call it for the time being C11, C12, C13, C21, C22, and C23, and C31, C32, and C33. All right. See, this is a first order, a 1x3 matrix. This is a 1x3 matrix. This is a 3x3 matrix. You see that?
Yeah.
So this is not the same order. This is a different order. This is a higher order.
Okay, cool.
All right. So once we get into this type of matrices, then we need to have something so something that has 4 dimensions, a 4th dimensional quantity that can connect them.
Yeah.
All right. Now, this is called tensor. This is what we call, I mean, you probably have done some of that in concrete. We call this the constitutive relation. It is the relation that connects the strain and the stress. So it's basically, if you have a force applied on the material, how the material would respond. So the response of this material will depend on the material properties, which is described by the CIJKL matrix. All right. So this is how it connects. This is the most general case. Now, for the time being, for the vast majority of the applications you will be working with in your life, I suspect probably the vast majority of you will not need this. All right, since the vast majority of you will be working with something simpler. Now, in the most general case, I said we have 9 components for the stress, 9 components for the strain, and 81 components for the material properties, 81 components. Okay? But now you have been using something like this in the past. So you have used something like this in the past. And in this constitutive relation you have used in the past, you did not use 81 independent components. You have used less than that. I would say much less than that. Tell me, or probably any one of you could tell me, how many actually independent components do you have in the CIJKL? How many independent components actually you have used in the past? Anyone can tell me? So in the most general case, we're talking 81 independent components. Now, how many components you have used in the past? In the 3-dimensional case, think in 3 dimensions. It is actually the 2. So it is only 2. So this is the elasticity modulus and the Poisson ratio. Now, how is it possible to move from 81 components to just 2? All right, so we make assumptions. So the first assumption, we assume that the material is homogeneous. All right, so this is elastic. Obviously, yes, correct. Any other things you can think of? Isotropic, yes, exactly. Isotropic as well. Again, homogeneous would mean that the material properties would not change. I probably just need to do something here. So you have a piece of material, and then the material property is homogeneous so that the material property would not change from one location to another location. So when you move from one place to another, so if you move from here to here, you'd have exactly the same material properties. Think about steel in this case. So the steel, if you have a piece of, or if you have a steel beam, then the properties of this beam should not change when you move from one place to another. Now, in the most general case, you can make an assumption that this is true for steel. But if we think about the concrete, for example, then the concrete would change every single bit of it, every single piece of concrete would have different material properties, because you realize that there will be aggregate in there. And the aggregate will behave different to the cement, will behave different to the reinforcements, and the reinforcements on the bonding phase between the reinforcement and the concrete, you will have even different properties. So concrete is heterogeneous, is not homogeneous, whereas the Steel, for example, is homogeneous. I mean, there will be small changes in the properties of steel, even if it is homogeneous. There will be some changes in the properties, but you can assume that in general, that it is actually homogeneous. Now, isotropic would mean that the properties would not change with direction. Again, think in terms of the steel. So if you try to pull this thing in this direction and you figure out the stress and then you figure out the strain, you'll see that this is going to respond exactly by the same amount compared to applying the force in this direction. So basically, you change the direction of the force, but the response of this material will not change. It will always respond in the same way. All right, so this is isotropic. Now, isotropic, so the material properties would not change with the direction, and homogeneous, so the material properties would remain the same at every single part of this material. Okay. Now, if you make these assumptions, so you will reduce this material or this constitutive relation into only three components. Oh, sorry, only two components. Now, based on these assumptions, you can also figure out that this stress and the strain tensors are basically symmetric. Sorry. So these components are equal. So this one is equal to this one is equal to this one, and this one is equal to this one. So this is symmetric, and then instead of actually having to write all of them all the time, you pick only half of them. I mean, not only half of them plus 3. And then you write them in a vector. So instead of writing the full thing, you will just write the 6th component. Now, this is the first reduction. And in order to get rid of this 4x4 matrix that is really difficult to write, we just end up writing a matrix that is 6x6. Now, you have 6 independent components for the stress and 6 independent components for the strain. And then in this case, if you want to connect them, you can connect them through a 6x6 matrix. So this is sigma x, sigma y, sigma z, x, y, x, y, z, and z, x. And this is equal to the strain on this end. I'm just going to write it here, not the full components. And here you have a 6x6 matrix that would connect the strain and the stress in 3 dimensions. All right. Now, I have in the lecture notes this 6x6 matrix. Go and see that if you may. But for this lesson, for this class, for this lecture, I'm not going to discuss the 3-dimensional case. I'm going to discuss only the 2-dimensional case. So if we are discussing the 2-dimensional case, we are going to reduce the stress even further to only sigma x, sigma y, and sigma xy. So this is 1, 2, and 3. Is there any questions? All right, so again, if you don't have any questions, if you mute yourself so that you don't add noise to the recording. Okay, so we are not going to work with this. We are going to even push it further. And this push further would reduce the stress vector to only sigma x, sigma y, and sigma z. And then the strain, on the other hand, will be epsilon x, epsilon y, and epsilon z. Okay, now, in order to be able to do that and still produce any meaningful results, xy here, xy, and this is xy. Yes. Okay. So in order to be able to reduce these stresses or these strains, you need to do what we call a plane stress scenario or a plane stress, or plane strain or plane stress scenario. So if you go for a plane stress case, you can assume that all the components of the stress that are happening in the third direction are equal to 0. And if you look into the plane strain case, you assume that all the components of the strain that are moving in the second direction are 0. I'm going to explain how this is, what this would mean. First of all, I'm just going to show you the relation of them. So this is sigma x, sigma y, and sigma xy. And this is epsilon x, epsilon y, epsilon xy. I mean, you can refer to the shear component using tau and gamma if you want, but I'm happy to call them sigma or epsilon. So it doesn't make any difference at all. All right. So if we are talking about a plane stress case, so in this case, we are talking about plane stress, and then all the components of the stress in the third direction, so basically all the components of the stress, which include z in them, would be equal to 0. So sigma z is 0, sigma x z or zx is 0, and sigma y z is 0. So all these three components are equal to 0. And then the relation between the stress and the strain can be expressed in this way. And you have in this case, I mean, this is something probably would sound a bit strange, but in this case, we are talking about plane stress, but we still have a strain component in the z direction, and the strain component in the z direction will be related to the normal stresses, x and y. So having the stress to be 0 in the third direction doesn't mean that the strain is also 0 in the third direction. All right, so this is important to remember. And then we have a plane strain case. In this case, we assume epsilon x is epsilon, not x, epsilon z is equal to epsilon. Zx is equal to epsilon y. Yz is equal to 0. And then in this case, the relation would change into this here. And then in this case, we also have a component for the stress, and the component of the stress in the third dimension is not going to be 0. Sorry, this is meant to be epsilon and epsilon. It is only related to the strain in the third dimension. All right, so I'm just going to explain that, and once I explain it, you probably see why the component is not going to 0 in the third dimension. Yes. All right. So if we're talking about plane stress, if we're talking about the plane stress case, then you can think about something that is really thin. So for a plane stress case, you are talking about something that is very thin. Now, it has to be thin. And then on top of that, you need to have the mid-plane. So basically, you can make the assumption that the components of the displacement, sorry, not the displacement, the components of the force that is applied are all applied at the mid-plane. And you assume that across the thickness, the material properties will not change. So it is something that is really thin. The material properties would not change across the thickness, and the forces are applied within this plane. So you cannot have forces applied outside this plane and assume that this is going to be a plane stress case. This is not possible. It will have to be always applied within this plane. So all the forces would happen inside the same plane. Now, assuming that everything is happening within the same plane, and it is a very thin problem, then in this case, I mean, thickness, of course, is small in terms of the other two dimensions. So it doesn't have to be really thin. I mean, just that it is really small relative to the other two dimensions. So if we're talking about a slab, for example, in a concrete slab, for example, in a structure, then in this case, this can be treated. I mean, it depends if you don't load it in the vertical direction. Okay, so this can be treated as a two-dimensional problem, but if you have the loads in the perpendicular direction, this cannot happen. But from the thickness assumption, this can be satisfied. This would be fine. Okay, so all the forces would need to be applied within the same plane, and the material properties would not change across the thickness. All right, if we have these assumptions, then we can neglect. I mean, of course, there will be components of the stress in the z direction. Of course, sigma z is not going to be 0, but it's just going to be much, much, much smaller than sigma x or sigma y. So it is negligible. All right, so this will enable us neglect this one and make it equal to 0. Now, the same is also true for the shear component. So the shear component Zx and Yz are also equal to 0 because they are small to the extent that they are negligible. Now, as you increase the thickness, this component will grow, and then at some point you cannot neglect them. You have to consider them. But if it is small and the forces are within the plane, this would be fine if you neglect them. Now, the strain component doesn't have to be doesn't have to be negligible in this case. You can imagine that it is possible you have deformations that will go outside this plane, for example. And this will make the strain in this case not negligible in the third direction. It is only the normal one, but it can happen. So there's a certain amount for that. And the amount is small if you compare to the other strains, but not negligible. Now, the plane strain case is the complete opposite. Now, the plane strain case is a situation where you have the material to be too thick. Now, I'm thinking if you, for example, if you consider a problem of a dam, for example, if you have a water dam and the water dam is really long, I'm talking about probably the dimensions in this case, we are talking about probably 10 meters, and then this will be probably 20 meters. But then the length of this dam, we're talking about probably 2 or 3 kilometers. So it's huge. So the third component of this, in this case, if we assume that the third direction is huge, then in this case, you can assume that the strain in the third direction are going to be 0 in this case. Now, think about it this way. The material is, the object is so thick in the third dimension, and it's going to be impossible to deform it in the third dimension. So this is the reason why you have it really strong, and you make the assumption that the strains in this direction are going to be 0. Now think about it this way. So this water dam, you only take a slice of that, and this slice would be representative. You usually take 1 unit, so probably 1 meter slice, and analyze that. And this one slice will be representative for the entire thing, because this one slice will only again deform within the same plane. If you want to look into the assumptions, again, all the loads will need to be applied in a perpendicular direction to the large direction. So basically, again, everything will need to be applied within the same plane. So these forces, the water, for example, pressure, is going to be still within the same plane. And the second or the third dimension should be really large. So the very large to the extent that these strains are going to be negligible. So I'm talking about epsilon z, epsilon x, or zx, and epsilon yz are equal to 0. Okay, so this is 2 relevant cases where having a 2-dimensional problem will make sense. Other than that, the 2-dimensional problem doesn't make any sense. So as we discussed the 1-dimensional case, we said that we're talking about a beam, for example, a cantilever. So the cantilever will be really long relative to the cross-section. So if we're talking about a cross-section, probably 0.01 meter, then the length is going to be 10 meters, for example. So in this case, you can neglect the 2 dimensions here and think about this as 1 dimension. If we are talking about the 2-dimensional case, the 2-dimension will need to be really much larger than the 3rd dimension, or would be much smaller than the 3rd dimension. And then in this case, you take one representative slice. So you slice this, and you take one representative slice, and you assume that all the other slices would behave exactly the same. Now, if you make these assumptions, you can work in a 2-dimensional space. If you don't have that, this is not going to work. You cannot work in 2-dimensional problems. Okay, so the 2-dimensional problem, this is something I really want to stress. The 2-dimensional problem would only work based on these two scenarios. Other than these two scenarios, you will be making probably a very crude approximation, and your approximation will not be correct. It will not be representative for the real problem. Okay, so if you make these assumptions, then the relation, the constitutive relation, would reduce to this one or to this one, based on what you choose, if it is plane strain or plane stress. And then I want to come here to the. So then you come here, and when you build your stiffness matrix, you pick the correct D. I've called it D in the past. I probably just call it C now if you want. I think C would be more relevant here since we have called everything C there. Just remove this here and put a C instead. So if we are talking about a two-dimensional case, then the C will need to be picked correctly. So you pick either this one if you have plane stress, or this one if you have plane strain. So this is the first thing that is going to change. All right. Now, if you look inside this, you'll see that this is, I mean, it is a 3x3 matrix. There is 9 components to that. First of all, it is symmetric. So this is equal to this, and this one here is equal to this one. And second of all, it only depends on 2 things. It is the elasticity modulus and the Poisson ratio. It's just 2 independent numbers in there. Everything else is related to these 2 independent numbers. The same is true also. I mean, the matrix would look different. So the material would behave differently in the plane strain case, obviously. But it is also only dependent on the elasticity modulus and the Poisson ratio. Okay, so 2 independent components. And if you look into the 3-dimensional case I told you about in the lecture notes, you'll see that this is also 2 independent components. Everything else is connected to them. So only Poisson ratio and elasticity modulus can change. Everything else would have to be dependent on them. All right. So this is how you build your stiffness matrix. This is how you build your stiffness matrix. You pick the right C. Now, just as an exercise, just to get you practicing, I want you to try and use this constitutive relation. Again, just to digest the information. So we have the strains. You have epsilon x, epsilon y, and epsilon xy. And I want you to calculate the component of the stress. All right. You have the elasticity modulus and you have the Poisson ratio, and I want you to evaluate the stresses. So I'm going to give you 5 minutes. This is really easy. It's just a straightforward multiplication. But I want you to just do that just to get your hands into the